Don't get your hopes up after that intro. Yeah, so we're going to talk today about Paleozoic orogenies in North America, and really from the view of the basin back to the orogenic belt. So that'll be the theme. So the objective is to kind of look at the timing and magnitude and as one linked system here. And the challenge is that first and foremost, the ongoing deformation exhumation of these orogenic belts destroys a lot of the evidence that you really want to have about timing and magnitude. And this is especially true in ancient and these complex multi-phase systems, which this is. So thereby the basin, which is often better preserved, can contain a more complete response of the record of the mountain building. So we're going to look at a detailed history of flexural subsidence and other subsidence mechanisms by geohistory analysis, essentially calibrated basin models. We're going to restore missing section, and we're going to quantify the tectonic load and topographic uplift by 2D modeling of the flexural effects based on stratigraphic cross sections. And we're going to evaluate other indicators of flexural effects, such as clastic alluvial wedges, steep margins, evaporites, source rocks, etc. So if any of this is any good, I'd like to acknowledge these people, but I don't want to blame them if it sucks. But I especially want to cite Trey Sessoms, who's a grad student at U of H, who's just finished up. And so I'm leveraging some of his work in the Southern Appalachians that Maggie Curry and myself helped advise him. So a few excuses here. This is a work in progress in some cases, although the Appalachian part is pretty mature. So I'll spend most of the time on that. I'm sure there's people listening who know more about many of these systems than I do. And obviously a lot of publications been leveraged, but there's some, I'll highlight the original new work. So the themes are that we can make inferences of plate geometries and trajectories from the basin observations that we make in terms of subsidence and paleogeography. We also see plate scale kinematic linkages that are indicated by synchronous timing at a continent-based scale. And I'll especially highlight the latest orogenies, the Veriscan, Appalachian, Ouachita, and Ancestral Rocky Mountains. The thick late Penn and Perm 4 deep sediments of the Appalachian and Watchtoss systems have mostly been eroded, but we can successfully reconstruct them with some confidence from basin modeling because we have very good surface coal rank or vitrinite reflectance data. And what we see is that there's common ties of these subsidence events associated with mountain building to source rocks, evaporites, and these basin margin wedges. So this is kind of the playground, if you will. And these are the basically the frontal deformation zones shown in red here of the southeast margin forelands, the Appalachian Ouachita, Marathon, and this kind of mysterious Sonoran megashear that I really don't want to talk about. And then the Antler Liard system on the Pacific margin, present day Pacific margin. So we're going to start out really with the Appalachian system and spend the majority of the time on that. We'll revisit this chart. I just want to explain it here and give you an idea of sort of the complexity across this whole system. The vertical scale is geologic time. This is roughly from east to west in a very general sense. And these bars represent periods of relatively fast subsidence. Where they're wide, it's kind of the fastest subsidence event for that particular basin or subbasin, and where they're thinner is where there's significant subsidence, but not as great as with the thick bars. And then this area here is where the section has had to been restored because it's been eroded at the top. So we'll start here with the Appalachian systems here. And this is just a quick summary of the plate tectonic setting for the Appalachian orogenies. There are 4 orogenies that have been recognized in the Appalachian system. In the middle to late Ordovician, we have this volcanic arc, including the Chapawamsek system and some other arcs that have been identified in outcrop that basically collided with Laurentia. And so that's the Taconic Orogeny and the first of this. And that basically encompassed the closure of the Western Iapetus Ocean. And then probably the least appreciated one is this microcontinent of Gandaria, which is thought to include a microcontinental fragment and associated arc and back arc. And that collided with Laurentia in the late Silurian, and that's called the Selenic orogeny. In the middle to late Devonian, we have the Avallonian, the Akkadian orogeny, where Avallonia, which is and Baltica, which is essentially northern Europe, collided with these terrains that have already been welded on with the rest of Laurentia. And that's the final closing of the Iapetus Ocean. And then finally, the Assembly of Pangea, if you will, is when we have Gondwana. So that's Africa, Southern Europe, it's called Amorica, and South America collided with Laurentia. And that happened variable in time, as we'll see, but generally Pennsylvanian through Permian. And that's the final closing of the Rheic or Paleotethys, as it's sometimes called. And we have these two sutures here that represent where those terrains have been welded on. So this is kind of the essentials of the database. There are 11 stratigraphic cross sections, 4 very good published USGS ones and 7 new ones shown in the white lines. There's an additional correlated wells in between. There's 12 calibrated basin models, and there's 17 flexural profiles along 5 different transects that are shown in blue. The Appalachian system, we have the preserved foreland here. The red line is the deformation front. We have what's called the valley and ridge, which is folded Paleozoic sediments. And then the brown line demarks the boundary with the Blue Ridge and the Piedmont, which is basically the metamorphic and igneous core. And then outboard of this yellow line, we have cover with the coastal plain Mesozoic and Cenozoic rocks or sediments. So let's take a look at this cross section. This is a colorful one from the USGS, kind of in the middle of the basin. Goes from Ohio through West Virginia. And so here's the cross section, and you can see that this is the Precambrian basement down here. There's an early Neo-Proterozoic to Cambrian rift event, like we see over much of the margins of North America. But then the 4 orogenies we're talking about are shown here: the Taconic, the Selenic, the Akkadian, and then as you see, the Alleghanian is only partially preserved. So here we have the undeformed foreland, this wedge thinning up into what would have been the forebulge position. And then we have the valley and ridge, where we have these thrusted folds, chord folds that stretch for almost 200 kilometer widths in some places. So we're going to look at a 1D basin model from this well right here. And so just to introduce this, because we're going to see a lot of these, so I hope you like it. Otherwise, you're going to be really sad. This is a geologic time on the horizontal axis, subsea depth on the vertical axis. And so these are all Petromod models that are decompacted. And what you see here is 1, 2, 3, 4, 5 subsidence events. And those comprise a rifting post-sag phase. And then these are in order: the Taconic orogeny in the middle of upper Ordovician, the Selenic, a very short event in the upper Silurian, the Akkadian in the middle to upper Devonian, and then this Alleghanian event. And we'll see that's kind of variable in time, but it's basically mostly Pennsylvanian Permian in age. So they can all be recognized and quantified by an increase in subsidence rate. They're all consistent with a flexural load origin. And I'll show you, we can very successfully model these using flexural modeling. And, you know, and of course, the thickest section is in the 4 deep. And these basin models all include some estimates of paleo elevation and paleobathymetry. In this particular place, we don't see a lot of subsidence associated with the earliest phase of the Alleghanian orogeny, so kind of keep that in mind. We'll also take a look at other tools to look at the basin response, such as paleogeography, et cetera. So comparing that with a basin model lying to the north, this is in Pennsylvania, we see the same 4 flexural subsidence events right on schedule. But when we look to the south, and this particular model is in Kentucky, we see an evidence of the Taconic, although it's a little bit younger, which is interesting. See no evidence of the Selenic or Akkadian orogenies. Very little sedimentation, very little accommodation space during this time. And we see the Alleghenian orogeny, but we see a much earlier onset of that in the Mississippian, basically the Chester, and that continues through the entire middle Permian time. So the Selenic and Akkadian orogenies seem to be restricted to the north and central foreland, and we'll see a very clear sedimentary response to that. And now we also see that the early phase of the Alleghenian orogeny, which is essentially the Watchtoss, is restricted to southernmost West Virginia through Tennessee. So this is a cross-section, a strike cross-section. This is from Trey's thesis that extends from New York down through Tennessee. And no mystery here. I mean, this is what drives most of the, along with decompaction lithology and paleobathymetry, this is what drives the basin models, is we see that these three syn-orogenic wedges along strike are thinning to the southwest. And so this taconic is still present. And so there still seems to be some flexural effect that we can model here, but the Selenic and the Akkadian become extremely thin. And so that kind of graphically shows it. And I think the other thing to kind of keep in mind, if we look at the age dates of these wedges, and we compare that with the sort of the interorogenic phases, which are shown here in white, there's as much time represented in these two intervals here as there is in these three intervals. So, this is actually kind of a classic flexural foreland. It doesn't get any better than this, much better behaved than, say, the Cordilleran system. So we've modeled this, and just as a review, flexure is basically, you can think of the big boy on the end of the diving board, and it bends down, and how strong that board is determines how much it deflects and the curvature of it, and how heavy that person is determines also how far it bends down. So the wavelength, if you will, from this foredeep, this flexural moat, is determined by the strength of the coupled lithosphere. And we measure that either through the elastic thickness or flexural rigidity. And I'm going to use elastic thickness here. And then the amplitude, how far it deflects, is determined by how large the load is, but it's also affected by the strength of the lithosphere, because how far distributed that is going to be depends on the strength of the crust. And then we have this forebulge, which is a very small deflection and hard to see, but it's usually about 5% of the foredeep. So we have a nice suite of stratigraphic control here in which we can define this curvature with these yellow points. And what we use is a MATLAB script that Joel Saylor wrote along with Kurt Sundell. And it's a inverse modeling Monte Carlo that is totally agnostic in terms of the key input. So it makes no assumptions on the strength of the crust, the size of the load, or the width of the load, and it iterates until it finds basically profiles and different load scenarios and different flexural strength scenarios that can fit those points within a set error criteria. So you run 100,000 trials and you see which ones fit. So we've done this in the Appalachian system and also in some of the Ouachita and Arm basins as well. And it gives very kind of sensible results, which is good. So I'm going to start with the Taconic Orogeny. Here we see the Appalachian foreland here. This is the present day deformation front. These are folded upper Ordovician foredeep strata, and we've made an estimate of where to restore the tectonic deformation front along this line here. And if anybody's got a question on that, we can talk about how we did that afterwards, because it's not easy. So this is a large event, and as we saw, it's present throughout, but it's focused more in the central and northern Appalachians, and it's related to this arc collision. And as we'll see, the Utica shale is deposited at the very initiation of this orogeny. And the outcrops of the Utica are up here in New York, wrapping around the Adirondacks. So this is a isochore in kilometers of the depot zone associated with the Ordovician. And we see almost up to a kilometer of section here. And again, this thins to the southwest. If we look at the distribution of the Utica, and this is from the Penn State group, which kind of is a center for researching these shale gas reservoirs. It's absent to the south, and the two thickest pots are in this northern and central area. We also see that this Martinsburg fleesh, which is a late Ordovician 4 deep fill, is best developed in this north and central area. And so we also can estimate along these flexural profiles biomodeling how much total topographic height would have been accumulated. And this is a little misleading because this is a dynamic system. So it's being denuded while it's being uplifted, but it gives you at least a semi-quantitative idea of the magnitude of the mountain belt. And we get up to some 3 kilometers of topographic relief on that to explain the flexure. So I want to riff a little bit on source rocks. This is from Ettinson in Kentucky. And basically he's showing the wedges associated with these orogenies. And you see is that the Utica here, shown as this black shale, is right at the onset of the Taconic, and then that wedge fills in with a lot of the 4 deep wedges actually back in the fold belt, not shown here because it's been deformed later. Then we have the Selenic, and we'll talk more about that in a minute. That's mostly a evaporitic fill. And then the onset of the Acadian is when the Marcellus was deposited. And we see the progressive infill of the space, of the accommodation space associated with the flexure, shown by this Catskill Delta. And what happens is that these source rocks, the Rhine Street and the Huron, or Ohio, if you prefer, kind of roll outboard from that. So they're sort of in the toe of the slope to proximal basin floor position. And as you fill in the space during the Acadian orogeny, they're displaced outboard in this kind of punctuated fashion. And so that kind of brings us to just to cite that a common theme that you're going to see is that one motif, it's not the way all source rocks are deposited, of course, but one motif is that these basin restricted source rocks often are deposited at the onset of the subsidence events associated with orogenies. So we have the Utica right here. It's right at the nick point for the Taconic orogeny. And then we see the Marcellus, the most important of these 3 black shales, so-called black shales, deposited right at the onset of the Acadian. So a general model is shown here, and this also is operative in sag basins and rift basins as well. But I'm showing it for a contractional margin. So this is in map view, and this is sort of a schematic cross-section. And what we see is that we get this initial subsidence event, and basically until the sedimentary engine can catch up with that space, we get a very large amount of space versus sedimentation. And that can lead to basically a condensed section at a second order scale, at a very sort of large scale, not at a eustatic scale. And then this increased relief here would possibly be potentially favorable for upwelling. We get runoff from the rising hinterland. So that all would encourage productivity. And then another player perhaps that we see for some of these systems, certainly for the Devonian, is that there's abundant arc volcanism, and that's another potential source of nutrients for productivity. And finally, by virtue of this profile and the steepening of the margin, we can have an opportunity for disoxy to develop because of silling and restriction. So keep that general model in mind. And one thing I'll point out is that while sort of the second order maximum flooding surface here is generally synchronous, these source rocks can be very diachronous in age because they're responding to this dilution by this prograding clastic wedge. So the Selenic, I'm not going to spend a lot of time on. It's kind of a very modest little orogeny, very short-lived. Again, it's best developed in the central and northern Appalachian foreland. And if it's dominated by evaporative fill. And so it's very thick halites and usually rimming anhydrite, and then eventually you get into evaporative dolomites, et cetera. And so this is an isochore of just the net halite that we see in the northern and central Appalachian foreland. This is where the mountain belt was. You see now we're getting much smaller topographic relief. And synchronous with this, we have deposition of the Salina group also in the Michigan Basin. and up to almost a kilometer of largely evaporitic sections cyclically punctuated with carbonates. So some have posited that this orogenic event at this particular time enhanced the aridity due to an orographic effect, essentially a rain shadow. And so let's talk a little bit more about this. What I find kind of interesting is that we can start to use these patterns to maybe infer where these plates were. It's very hard to kind of reconstruct these trajectories for the Paleozoic, and it's very incomplete exposure of the terrains as well. But what's implied here is that the southeast end of the Gandaria microplate would be somewhere in this position, because we're not seeing any mountain building effect here that would be collisional in nature further to the southwest. So let's compare these two basin models here. This one's from southern New York, and this is from near the center of the Michigan Basin. And what you see is that the Michigan Basin shows the largest subsidence event is right on time with the Selenic orogeny here. And so it's, I don't think that's accidental. And moreover, we see a taconic event and an Akkadian event. So these sag basins, I'm not claiming that we've solved the riddle, but they seem to be a very strong kinematic linkage that perhaps this deflection is being transmitted at a continental scale from the orogenic belt to this kind of classic sag basin. So we're going to move up to the Akkadian orogeny. This is the what's shown in green here are the outcrops because of exhumation of upper Devonian strata, and we go from kind of classic deltaic clastic wedge in this position all the way out through these distal black shales of the Huron formation. And the Marcellus, which is middle Devonian in time, is outcropping here. And that's where we've reconstructed the Akkadian deformation belt. So this is Icepack or isochore of the Akkadian. It's a very thick, significant event. It's over 2 kilometers at its thickest, and realize, of course, that foreland continued through this exhumed valley and ridge province here as well. If we look at the distribution of the Marcellus, same old story, to be a broken record. We see the Marcellus up to about 100 meters thick, is present in dominantly through Pennsylvania into West Virginia, and is absent to the southeast. So it's reflecting that space that was created by the orogenic event. And we're getting a mountain belt implied topography of, roughly 3 kilometers or so. If we look at what happened, so that's kind of in the upper part of the middle Devonian. If we look at the late Devonian, this is a paleogeographic map that Trey built from outcrop publications, but tied to a bunch of well-logged facies interpretations. We see that this Fomenian, this latest Devonian paleogeography, we have the progradation of the Catskill Delta, so fluvial through shallow marine, through offshore marine, to finally these dysoxic offshore black shales in this position. And so it's filling in that space in the same fashion. So I think it's pretty interesting that not only is the second order retrograde and associated condensed section best developed in the north, but that's actually where the most robust clastic fill is later, as we're denuding the mountain belt with erosion. And so here's the suture that from various publications that's been mapped, the Iapetus suture, where Avallonia and Baltica basically sutured on. And again, I think we can make an implication that the southeast end of the microplate may have been in a position such as here, as Britain and Scandinavia, and the extension of these to the present day southeast got welded onto Laurentia. So the last and most difficult one is this Alleghenian orogeny, and the simple reason is that most of the section has been removed. So this is the distribution of where the Pennsylvanian is outcropping in blue, and this purple is where we have Permian preserved. So only under this purple do we have the complete Pennsylvanian section preserved, and we have up to about a 1/4 kilometer of basal wolf camp, the Dunkard formation in this position. So the question is, how much more Pennsylvanian in these areas and Permian as well was present. And, it's obviously a difficult problem, but it can give us some insights into this last of the orogenies. So we have the luxury here of this really good USGS database of about 1,900 surface measurements from Pennsylvania and Permian coals. It's basically a kind of a coal study that was done. And those are all these data points here. And we can map the vitrinite reflectance. And you see it's even in this very thin outward part, we're in the oil zone at surface. So there had to be a lot more burial, and we're getting up to 1.5 RO in these more proximal positions. So we can obviously calibrate that. And so here's just one example that we have this burial and then some amount of exhumation. In this place, here's this most important surface vitrinite point. The subsurface data is not as good. It includes conodon alteration indices. If you put no exhumation here, you're like 0.6 RO too low here. But if you put about 2.2 kilometers of exhumation, you get a reasonable tie. And of course, there's going to be some error bars around this. And USGS study, which I've also leveraged, has come up with very similar solutions to this. Also calibrated to borehole temperatures, et cetera. So we've come up with these exhumation estimates here, and we estimate up to about 4 kilometers of section removed. And that ties quite well to thermochron and fluid inclusion data. This is the only kind of good point out in this area, but at least it's kind of directionally consistent. And of course, that as the wedge gets thinner in this direction, we see less and less section removed. So from this, we can reconstruct both the Pennsylvanian and the Permian Icepack, and this is just the example of the Permian. And we see that we get up to about 3 kilometers of Permian we would predict was deposited right in front of this Alleghanian deformation front. And we're talking about, again, about 3 kilometers of topographic relief. And the reason why this is important is just not in a pure science sense, which is how I've gotten interested in this, but this upper Pennsylvania Permian burial was important in maturing these gas shales. So without this burial, they wouldn't be in the current state, maturation state, especially out in these distal areas that they are today. So that is the kind of a quick run through of the Appalachian system. So we're kind of ended up here. We're going to talk now about the Watchtoss Marathon system and kind of quickly walk through, in the interest of time, the Black Warrior, Arcoma. Not going to talk much about the Fort Worth, but it fits quite nicely. And the Velvety forelands associated with this part of the belt here where South America ultimately collided. So starting with the Black Warrior, well, one thing we see on this, I'll say around this margin, is really variable fills in both the nature of the fill, but more importantly, you'll see the timing. So the Black Warrior is filled with this kind of prograding deltaic system. It commences in the upper Mississippian, and it's marked by this Floyd, this organic rich source rock, kind of a failed shale gas play. And then we got these wedges that come in through the Pennsylvanian that have these mappable and mineable, in some cases, coals through the Penn. And so this is an upper Mississippian through Pennsylvania system. We have to reconstruct this section. You see we get up to about 1.0 RO at the surface here. So that's what the Black Warrior looks like. And if we look at the basin models for that, on the left is the Black Warrior. And we see this onset in the upper Mississippian and the Chester at Floyd time. The Arcoma looks like it's just a little later. And so there's a little deflection here in Mississippian, but the fast subsidence really occurs in the Utica time. And so I'd like a little bit better calibration data here, but we're already seeing maybe some indication, some diachronity. I will point out the timing here, the Black Warrior, is pretty much on schedule with the Southern Appalachians in Tennessee and Kentucky. So that seems to be a linked system. So let's take a look at a schematic cross-section through the Arcoma Basin. So the growth really started maybe in the Moro time, but it's largely in a token and younger section. And we get this deeper water basin. I don't think it was really deep, but there's turbidites that were deposited in this. And then again, we have the same issue with a lot of section removed here, subsequent to deposition, both in the fold belt and out here in the foreland where we're about 0.8 RO. So the onset of subsidence is a shade younger here. We have a deep water system instead, or relatively deep water. And we had the same reconstruction problem. And so this is the reconstruction we've done. It's again up to a couple of kilometers of restored upper Pennsylvanian and Permian. How to balance that out between that is an open question, but something at least we can get a handle on. And then moving further along the margin to the Velvety Basin in front of the Marathon fold belt, we see it's an even younger flexural wedge, really kind of commencing in the upper Pennsylvanian now. And then again, you have these turbidites, these tight gas sands of the Ozona and Sonora deposited through the Wolfcamp. And again, while we have pretty much the whole Permian section preserved out here, these have been uplifted and eroded as we go into the foredeep. So again, there's some uncertainty with this youngest section. Basically, what I've done is to project these thicknesses into the fold belt and use what little calibration data there is, which is not great in this area. So that's the kind of a quick run through of the Ouachita Marathon. And Fort Worth is in between, the timing in between the Arcoma and Velvety. So if we take a look at this whole margin, which I think is better to treat as, even though these margins are really different in their expression, this is a big mountain belt and this is kind of wimpy, there seems to be some tie of the timing. And so we have the oldest onset of flexural subsidence in the southern Appalachians and Black Warrior Basin, and it youngs along the Appalachian system to the northeast. And you can see that on these plots here. And then similarly, it youngs to the west from the Black Warrior to the Arcoma to the Fort Worth to the Velvety Basin. And you see that very clearly here. So perhaps, that's telling us something that there's a postdoc and a PhD student that's been in contact with at U of H and New Mexico Tech that are really interested in kind of coming up with some improved geodynamic models to kind of understand these plate trajectories and what's going on. But maybe this acted as kind of a first contact here with Gondwana, sort of the indenter. And this is a little different story than what you read in the literature. So I think it bears some further evaluation. So let's talk a little bit about an even more complicated system, the ancestral Rocky Mountain basins. And so that's all of these basins in sort of mid-continent through the Southwest, shown here in blue. And so now we're looking at isolated basins and basin-involved uplifts that are in the Southwest and Central area. They're kind of, and if I can use the term with some trepidation, they're sort of Laramide style. They're thick-skinned. We see a tremendous variability in the basin fills, and we also see some variability in the timing. But overall, we're looking at something that's roughly coeval with the Alleghenian and Ouachita Orogeny, Pennsylvania and Permian in age. So I'm going to start with the Permian Basin because we got the most direct link between the Velvety and the Delaware and Midland basins, and we'll talk a little bit about that first. So, let me go through this. So we saw this younging of the Alleghenian and the Ouachita away from this kind of far south Appalachian Black Warrior system. And now we're going to take a look at these basins here. And you can see that they range from being quite young with the onset of subsidence. If we look at things like the Oro Grande and the Pedregosa, as well as the Permian Basin in the sort of upper Penn, Des Moines, Virgilian age. And then there can be significantly older things like the Ochre and the Eagle Basin, the Paradox, and then older yet in the Anadarko and associated Hardeman basins. So to go back to reprise the discussion on the Watchtoss system, these are all the basin models from the Ouachita basins, excepting the Velvety, which kind of sticks out like a sore thumb as being a younger rapid flexural subsidence here. And if we look and overplot the Velvety, now shown as this dark blue line with the Permian Basin, we see that they're really pretty much synchronous, that we're talking about upper Penn, largely subsidence, some subsidence in the Mississippian that you see here, but mostly uppermost Pennsylvania. And what is really different about these systems is that during this phase that I'll call the marathon phase for this family of basins, there's a strong differentiation. So things like the Delaware and to a lesser extent, the Midland basins are going down. The platforms such as the Northwest Shelf and the Central Basin platforms are subsiding less rapidly or even uplifting, as we see here at this site. So this kind of differentiation of the basin is really important in these systems. But the next thing that's interesting and that I'm really interested in trying to understand is the subsidence post this differentiation phase, when we have the thrusting going on in the marathons, and as we'll see, also deformation out in the Permian Basin. And these are all subsiding, whether you're on a platform in the basin, at about the same rate. And this has a paleobathymetry pretty carefully calculated, and that's really key in this case. And so I'm going to riff a little bit on this kind of transition phase. It's at the lower, some people put this at the top Penn, but it's really in the basal Wolfcamp and lower Wolfcamp unconformity, when things really change from this differentiation phase to this long wavelength subsidence that perhaps is a mantle-related process, dynamic, if I can arm wave. So this next is some gratuitous animation from outcrops. Sacramento Mountains is between Cloudcroft and Alamogordo on the top, and the Waco Mountains on the bottom. And so what we see first on the top is that we've got these dipping beds with what look like a structural growth strata in the Holder Formation. And then we got these much more flat-lying, undeformed units in the Abo, and then finally the Lenardian Yeso above. And if we just pan to the right, you can see this is basically an anticline that's been beheaded by this lower Wolfcamp unconformity. And we see a similar thing on the Diablo platform in the Waco Mountains. And we see this, as you'll see in a minute, on the Central Basin platform, is that we get these dipping beds. This is now a token in age. These are these cyclic ice house carbonate clastic cycles. And then we have this lower Wolfcamp unconformity with what's called the powwow conglomerate sitting on top, and then the carbonates of the Waco above. And again, so there's a large tectonic unconformity at a coeval position. And what we see on deposited on top of that are alluvial fans, sort of cobble size fans, as you see in the lower part of the Abo Formation, and also in the powwow conglomerate. And then really importantly, a relatively undeformed section above. And so this is this transition from this short wavelength differentiation, subsidence, and uplift to a long wavelength subsidence that's encompassing a larger area. And there's a published seismic line across the Central Basin platform. So here's this lower Wolfcamp unconformity. You see the thrusting and the folding. And then above, while there's some folds and some draping over this, it's much less deformed than it is at this. And so you're stacking a relatively thick section of upper Wolfcamp through Guadalupean strata on top of this, even on the highs. And then if we compare this and contrast it with the Anadarko Basin, so we got this young Virgilian, say, through Wolfcamp tectonic subsidence, and then we have this longer wavelength upper Wolfcamp through Guadalupean subsidence. Anadarko, we're looking at a much older system. And so the commencement here, and so we got relatively deeper waters here with some turbidite deposits, and then the famous granite wash, this alluvial fanglomerate apron feeding out into that. And we see the subsidence commences in Mississippian time. And you see that on this geohistory plot. And here we have pretty much almost the whole section is preserved. So we don't have the issues that we have in the Appalachians and Watchtoss. So very different timing on this. Even though if we look at some of the fill patterns, they may look superficially somewhat similar. So we can actually map the distribution of the onset of this subsidence. And we already talked about this old to young pattern here and this old to young pattern here. But within the arm, we also see that most of it's kind of in this Pennsylvanian time, but we got this older Mississippian onset here, and we see these associated basins in the Oro Grande and the Palo Duro and the Delaware Midland is all quite young in terms of its onset. So I think there's a linkage here. I don't yet fully understand what's driving this. I have some ideas, but I'm not brave enough to pose them now. And then I'm going to close with real quick with the Antler orogeny, the most poorly understood. It's Middle Devonian to Mississippian on the western margin. And the real issue here is that there's all this later overprinting of the Sevier and the Laramide, and then of course the basin and range. And so where this foreland is all been hammered by Cordilleran and later basin and range deformation, with the exception of the Liard Basin here. So if we look at the subsidence patterns of the Liard, and then here's one out in the Western Canada Basin. And then interestingly, the Williston, we see this roughly Middle Devonian through Mississippian subsidence that's coeval again with this Sag Basin lying out in the basin. So, and interestingly, the Nesson Anticline, which is the only real structural feature, has mostly been interpreted as being a Devonian structural growth on it in the Williston. And this Horn River is, you probably have read about it. It's a important gas shale target. It's in kind of a remote area, so it's got some other economic issues. But you see that on this cross section here, as we go from the North Alberta Shelf through the what's called the Horn River and the Liard Basins, we get an expansion of the section and development at the onset of subsidence of these Horn River shales, the Musqueam, Otter Park, and Evie, that basically pinch out into this carbonate platform of the Slave Point and Keg River as we go up dip. So that was a lot slides, but in summary, I'd like to say basin response, I think, is a somewhat underutilized indicator by kind of your classic, people who look at mountain belts. And I think it's got a very complementary aspect to more direct techniques of looking at reconstructions and structural growth strata and stuff like that. And so especially in these ancient systems, I think it's a really useful thing to do. We see these genetic linkages at the plate scale, and I think these are best treated as whole systems and not like I'm going to look at the ancestral Rockies or I'm going to look at the Watchtoss. I think there's a strong linkage there. And interestingly, there also seems to be a linkage, and we see this with the Illinois Basin too, by the way, that there's a synchronicity between these sag basins and the thick skin deformation associated with the arm and these marginal orogenic systems. And then a lot of important petroleum system play elements can be directly linked to these large scale tectonic controls. And most notably, I kind of highlighted marine source rocks. And that's all I had. So thanks.
Cool. Thank you, Kurt. If I can get you to stop sharing your screen.
I will.
We have some questions that have come up in the Q&A, and I am happy to, the first one is from Lawrence Walker. You can see them as well. And no, I did not prompt him, so as well. Kurt, can you see them? You can see the questions, right?
Yeah, I just pulled them up.
Okay. So Lawrence, I can actually turn.
I saw Molly Turco's talk at the RMAG meeting. And yeah, so when you kind of zoom in, and actually this PhD student in Socorro has worked the Anadarko from a very different point of view. Yes, there's clearly a transpressional aspect to that. So there is, I agree that there's an oblique aspect to a lot of these things. And I think it's an interplay between perhaps a rheology of the different elements. There you have the allocogen that became the Wichita uplift and the impinging, stress direction. And so that's why, and similar issues arise with the Laramide. That's why I think we're seeing all these cattywampus orientations. Some are oriented north-south, some are east-west, some are like the Uncompahgre, it's kind of northwest-southeast. And so I think there is a lot of, I don't like sort of long strike slip zones, but I think associated with each of these basins, there's going to be shear. And Anadarko, I think that's been pretty well accepted for a long time. And we also see shear in the Permian Basin with the Grisham Fault, which is an east-west fault. So I think that's going to be an ongoing theme. So I hope that answers that.
Yep.
Oh, a compiled bibliography. Wow, that's
right. Yeah.
Not right now, but there will be a lot of these for the Appalachian system will be in Trey Sessome's master's thesis, which has been approved. So that I can with his permission, I could probably excerpt. Universities are really funny about putting anything out there before it's stamped approval, but I could excerpt that bibliography, which is Appalachian centric. That would be a good start, at least. Okay. Yeah. So the Permian Basin. Oh man. Yeah. So what I think is really interesting about the Permian Basin is that you have, it's basically a three-phase system in my mind. Is that you've got, the Toboso Basin, which is this kind of very low relief, and you get, the Woodford and Barnett. So very stinky little pots, nice carbonate reservoirs. And then you put on top of that, you get all this deformation associated with this contractional event that commences in the Carboniferous. And so you deform all that stuff. And at that time, you're also putting this huge pot of Wolfcamp source rock, which is again at the near the onset of that. And Wolfcamp D is actually Pennsylvania, as most people know. It's Virgilian. So this Virgilian through Wolfcamp section, I mean, it's a perfect situation because you've got these stinky pots of thick shales. You've deformed these older ones. They've got reservoirs and source couplets within it. And so you got a lot of different positives going on that. And the fact that it's an arid system is not a bad thing either, because then you get some super seals in the younger Leonardian and Guadalupian platform carbonates. But that's a whole talk in itself. So
hey Kurt, before you go on to Luke's, there's actually one in the chat from Dale Bird.
Okay. Yeah, let me
read it to you.
He
said, Kurt, excellent talk. Do you think that Perigondwana terrains extending southwest from Avalonia, Florida, Yucatan, the one I can't pronounce, and possibly the crust beneath Sabine and Wiggins uplifts may be causing some confusion? Also, do you think that the indenter is a syntaxis?
Okay, I don't even know what that means. So I'm
neither do I.
I'm embarrassed. Yeah. I'm embarrassed about that. So I don't know. These things like the Sabine uplift are actually on schedule with this Upper Cretaceous igneous event. That's really important. So I think there's another player in there. Things like the Jackson Dome, et cetera. And there's actually intrusives have been dated on that. But I can't question that there's rheology in all these terrains that were docked. And really the hard thing is that I've looked at tons of papers and everybody's got a different model of where the terrains are. I mean, they agree on like the Acadian is in New England and in the Maritimes, and they're pretty good with the Gandaria domain in the Maritimes. But it gets, and then the abducted arc is okay, but extending that underneath the coastal plain is hard work. Potential fields would potentially, I know Dale's an expert on that, would be helpful. And I think that's where the opportunity is maybe to integrate some of these basin response things, which I think are not, I hate to say it, not that interpretive. You got a big ass thick section one place, you don't have it in another place, it's telling you something. If you could integrate that with whether it's potential fields, structural restorations, and probably as important as anything, and I've looked a little bit into this, it's confusing, the metamorphic timing and igneous suites. You could probably come up with a refined story on these really old complex terrains. So I don't know if that probably didn't answer the question, but
no, that was good. You also answered, I can't, as host, I can't type questions in, which is really hard, but you answered one of mine, which was kind of where are you going to integrate some of these basin responses with other things to even better refine some of your estimates of uplift and erosion and thicks and thins. So that kind of answered that one too. Okay, so there's a question from Luke Wilson.
Okay, let me.
Can you see it?
It was a typical age uncertainty. Oh, okay. So
that was one of mine as well. So.
Yeah, that's a good question. What I used is for the Appalachians, which is the most mature. Right or wrong, I took the USGS chronostrat charts, which were all integrated over that whole area, and I converted that to the Ogg and Gradstein scale. And it's most of the marine ages are based on conodonts. And then it gets a little fuzzy when you get into the Potsdam and these non-marine sections where they're using palynology. And I would say plus or minus on a relative basis, plus or minus 3 to 5. And on an absolute basis, obviously it'd be more of that, but I'm more interested in the relative. One thing I would just caution is you can't go to any one paper and just take their ages out of there. You have to say, is this, mid-Stephanian, or, well, I shouldn't use European stages, but you can't use, because people are not always consistent over time on the absolute ages. So that's why I used Ogg and Gradsteins, which is the most recent. And they have all the paleo zones. If you're not familiar with it, you should look into this Timescale Creator app. It's really cool. It's got all of the bio stages in it, and it's kind of where I start a lot of times, because I can see the different ammonite or conodon zones or nanos up in the Cenozoic.
Hey, I was going to say, so not everybody saw the question. So Luke's question was, what's the typical age uncertainty on your geohistory profiles? Okay.
Yeah, that's what I tried to answer.
Yeah, no, I know. So go ahead.
Oh yeah, so uplift, timing of uplift. Yeah. I really, you don't get timing of uplift from basin models, as everybody knows. Basin models are, if you got really good maturity, it gives you it's kind of like a maximum temperature. It's a time temperature integral. So you can use sort of geologic context, or you can use thermochronology. And most of the thermochronology that I've seen, and there's a fair bit, but it's mostly back in the fold belt and even into the Blue Ridge in some cases, but mostly the fold belt, indicates that there was kind of continuous uplift. And that'll just tell you when it passes a certain time. And I think Triassic doesn't feel bad to me, because a lot of people think that the transition between the Blue Ridge and the Piedmont is the rift shoulder for the opening of the Atlantic. And you get these little Triassic rift basins in there. So it could be a rift shoulder uplift. I don't think there's a lot of possibility of any Triassic fill on the other side of the drainage divide, but we can have that debate. So we kind of assumed a fairly continuous exhumation and erosion. One thing we were pretty careful about is you see a lot of basin models that they just use measured depths, and that's, for this purpose, that's garbage. You got to use elevations. Some of these things are, they're sitting at a kilometer in the arm basins above sea level today, and somehow they had to get to that position. So it's a hard question. It would be beautiful. You can't do it in these ancient rocks, but it'd be beautiful. You had isotope logs for paleoclimate data to get paleo elevations, which they have done some in the Western interior, but I don't think you can do it in rocks these old. But that's a hard question on timing. And I think thermochronology, I know Maggie she's writing another proposal, and she wants to do more thermochronology, but more out in the basin. There's very little done out in the basin. It's all done in the deformed belt.
And then Jim Tucker has a question.
No, I don't. Not that I'm aware of. But if somebody has
the question, Kurt, can you repeat the question? Because not everybody.
I was thinking about the microcontinent you mentioned earlier on as well, to North America. Well, there's the Arc, which is at Chapawamsik in the Taconic. There's the Gandaria.
think that was
block,
it.
which is Silurian, and there's the Avalonia Baltica, which is the Akkadian, and then it's Gondwana after that. And the Watchtoss is basically the last kind of closure to form Pangaea with the Gondwana. So that's on the Watchtoss belt. That's essentially like Yucatan and South America, the southern parts of Gondwana, and for the Appalachian system, that's Africa, present day Africa. And pieces of that got left behind. And I know that they know that from dating and geochemically characterizing some of the granites that have been drilled in South Florida, that they belong with Africa. So there are pieces that are left behind, but I actually don't know. I'm sure somebody else knows a lot more about this, like what, you know, what's in, I don't even know what's in the Llano uplift, for example. And so I'm sorry, that's beyond my ken, so to speak.
And so I have, that's the last of our questions that were in. I actually have one kind of together, your thickness estimates from your modeling, your Monte Carlo modeling, which I thought was fascinating. Are those in a database that you guys are going to make accessible and shareable? Are you going to add some of those into the USGS database? And that follows with kind of where are you going next with all this?
Yeah, so we're going to have to publish something based on Trey and my work in the Appalachians that'll probably get some brutal reviews because Appalachian has been worked so long. Mm-hmm. And that would be the first thing because I think that's the most mature work. Okay. Trey's thesis, he did all the basin models and flexure models I showed were ones I had done starting 2 years ago. And he's done a whole nother suite of basin models and flexure models on top of that adds to that, but it's only through the southern part of the system. And that'll be in his thesis. Yeah, it's probably going to take a year to kind of get this out because I got to do this frontier paper first. But yeah, and anything we publish, we're going to have huge supplements. So, you know, all that data will be available. But if you're interested in that, I mean, I know there's a lot of attraction doing 3D flexural models. And Maggie wants to do that. And actually, I think Noah Hobbs at New Mexico Tech may do that for the Appalachian system. Look at the, rebound. That's another great question. Yeah. So we're going to try and model the rebound for the Appalachian system. I think it's the perfect place to do it. And I'm not sure it's rebounded as much as it should have. Then that's just a skeptic. Because I think there's too much preserved for what the topographic, I mean, Appalachians aren't that high, you know, it's like 5,000 feet maximum height, and that's a huge wedge. So we're going to try and model that and see if there's hysteresis or not. And that would be extremely controversial. Yeah. But yeah.
So I know we're running a little bit long, but there are a few more questions that have popped up. And so I want to give you the opportunity to answer those. I know there may be some people that need to sign off.
Oh yeah, no, people can leave. So.
Totally expect that, but we do have William Morgan ask, given the volume of kudos, very informative talk. Given the volume of Permian rock stored in the Appalachians, where were those sediments deposited?
Where were they deposited, or what happened to them? You mean? I mean, they would gone out the Mississippi system. I think one thing that again is probably I've only come to appreciate more recently is that we kind of look at these flexures as a zero-sum game, but if you look at modern ones such as the Andean, I don't like the Himalayan as much, but the molasse even, neotectonic ones, there's a huge alluvial wedge that's built up. I mean, if you go to the foothills in the Andes, you're sitting at 8,000 feet. And so that's a huge alluvial wedge. And so we've tried to honor, and I measured the slopes, and they're very, very modest to build up a big alluvial wedge. And if you look at the whole Appalachian system, it's kind of a grossly retrogradational through these orogenies. And so the last wedge, the Alleghenian wedge, appears to be all non-marine. And the Akkadian ended up as mostly non-marine at the end. And so, yeah, I don't know if that answers, if that's the question that was asked, but I mean, we think we can reconstruct where they were from the basin models, and that's what I showed with the Permian Icepack. But some of that thickness is actually it's not all building down, it's also building up. I would propose to some extent.
William, does that, if that doesn't answer your question completely, Kurt's email address at his U of H and Rice, or I don't know if it was your personal, I don't remember which one was in there.
I think I gave my personal email. I mean, the U of H ones go get directed to that. I check my Rice email too, if you want.
Okay.
I see Nina's question. So yeah, I didn't talk about the Ellesmerian system. There's another Devonian one in the Arctic, and that is right on schedule with the Antler and the Acadian. So, you know, Ryan Lear, and I've seen, I've looked at Kepi's paper. I think that's one version of the terrains. I've seen so many different versions, but anyway, so it's Ryan Leary talks about during the arm that the continent was in a three-sided vise, and during the Devonian it was in a three-sided vise too. You had the Antler, you had the Acadian, and you had the Ellesmerian at the top. The Ellesmerian is very poorly understood. There's not a very well preserved foreland, but it is that same timing, and that to really go out on a limb, that linked Devonian system, I put this in my source rock talk at APG, might have been an influence on the widespread deposition of these uppermost Devonian basal Mississippian source rocks that are all over North America. If there's Fomenian section there, it's almost always a black shell. And so maybe there was a large scale restriction of the whole thing. So I couldn't put that in the talk, but that's not flexural. That's just, you know, kind of oceanographic effects. It just as a wild ass idea.
Cool.
Okay.
All right. I think that's, and thank you once again. I've thanked Kurt like 4 or 5 times now for giving this talk. As you can see from the attendance and the questions, totally fascinating. This talk will be available at HGS's website. We record these and we archive them, so you'll be able to access them. Kurt's information is available for follow-up questions and also ideas. Kurt is always open to ideas of new thoughts and ideas that could come into his work. So thank you, Kurt, very much.
Okay.
And
thanks,
we're going to sign off, and we look forward to seeing everybody at our events in January.
Okay. Thanks for the questions.